Today we're going to talk about continuity of functions. So in general, there's a definition for continuity. We say a function f is continuous at a specific point A if the limits, right side limit, left side limit, is exactly the same as the value of the function. So the limit and the value of the functions are matching up. For example, if you look at the graph number 1, if you look at the limit at the point A, what we get is if you follow the path along the curve on both sides, what you end up with is a certain y value, let's say f of a. The limits and both the value at that point, they're exactly the same as the value of the function. The limit on the left, limit on the right, and the value of the function, they all match up, and they're exactly the same as, in this case, f of a. If you pick numbers, this would be 1, and that would be, for example, 2. So the limit and the value of the function are the same. If you look at second graph, this is not a continuous function, because if you look at the point A, the limits approach to this number, let's say star, but at the point A, f of a does not exist. Since the circle is an open circle, that means at that point there is no corresponding y value. But the limit still exists and approaches to that star value. So the limit would be, let's say, limit f of x as x approaches to a would be star, but the value of the function does not exist. It's kind of, if you think about continuity, it means that if you start moving along the curve, you should continue and reach to that point and be able to continue without picking up the pen. So in this case, it's not possible because there is a hole in the graph and you cannot cross that point unless you pick up the pen. And if you look at the third graph, what you see is the limit on the left side and the limit on the right side, they're not equal to each other. The left side is a different value, let's say star, right side is a square. Therefore, star and square are not equal. Therefore, the limit f of x as x approaches to a does not exist. So therefore, we cannot talk about the continuity at all. Okay, so these three examples, you can think about the graph again as if you see a function that is continuous, that means you can graph that without picking up the pen. Okay, here's an example. And they ask you, where is this function discontinuous? If you can graph the function, you can answer this question. But normally, for rational functions, the function is continuous everywhere except at the point where the domain does at the x value where it doesn't belong to the domain. So here, if you find the domain of this function, domain of f of x is all real numbers except 3, since 3 makes the denominator 0. X minus 3 equals 0, therefore x is 3. At this point, 3 makes the denominator 0. So what does this mean? That if I ask you what is f of 3, you should say it doesn't exist, since you'll get a fraction with denominator 0. So I can say the function f is undefined at the point 3. So therefore, there should be discontinuity at x equal to 3. Is a discontinuity point. Any other point that you pick, let's say if you pick x equal to 5, for example, if you calculate the limit of the function, as x approaches to 5, what you get is exactly replacing 5 into the equation, 5 squared minus 5 minus 6, divided by 5 minus 3. What you get is 20 minus 6 is 14, divided by 2, you'll get 7. This is the same as exactly f of 5. So the limit and the value of the function are equal at x equal to 5. Therefore, the function will be continuous at that point. 5 is an example. Any other point will have this property. But the only discontinuity point is x equal to 3, since it doesn't belong to the domain. This is similar to this second graph. That point is where the function is undefined. So therefore, there would be no continuity at that specific location. Here's another example. Sometimes you deal with the piecewise functions, and if you look at each side, what you see is, let me graph this, maybe it would be easier. If you see the graph, then think about the function. Normally, you should be able to graph these piecewise functions as long as the functions are simple. X plus 3 is a straight line, it's a linear function. At x equal to 1, here's 1. X plus 3, graph x plus 3 everywhere. So here, slope is, this is y equal to x plus 3 if you've forgotten. Slope is 1, and this is the y-intercept. So a 3 is the y-intercept, and slope 1. That means move 1 right, 1 up. So you will get to 4. This is the graph of x plus 3. But what we want is not the whole graph. We only want the section where x is greater than or equal to 1. So I don't really care about this left-hand side of the graph. Okay? The only part of the graph we care about is the part that x is greater than or equal to 3. And at x equal to 1, it's acceptable, so it's closed point at that point. And y value is 4. If you replace 1 plus 3 should give you y value of 4. And 2x minus 1 is another linear equation. 2x minus 1. Slope is 2, y-intercept is -1, so I have -1 as the y-intercept, and slope 2. So move up 2 units, 1 unit to the right. So this would be 1. And this would be the other line. So this is x plus 3. This is 2x minus 1. Y equal to x plus 3, y equal to 2x minus 1. And you notice that the 1 I put an open circle, and this is just because there is no equality option. If you put a closed circle at this point, then you have 2 different y values at the x value of 1. So that is not possible since you need to have a function. Okay, so this is an open circle. Now, if I ask you where is this graph discontinuous, it's easy to answer. At 1, you have a jump in the graph. So you should say at x equal to 1. And this is kind of the whole idea is wherever this break happens, that you split the domain, or you have 2 lines. The lines are each one always connected. So there is no discontinuity in the line itself. But when you move from one graph to the other, there might be a jump in the function. So what you need to do is, in these cases, if you cannot graph the function, you should calculate the limits and say, okay, let's figure out what is the limit of f of x as x approaches to 1 from right side, as well as figure out what is the limit of the function as x approaches to 1 from left side. If these two are equal, then I can say, okay, the limit of f of x when x approaches to 1 is that number. So now if you look at the first one, what is the limit of the function as x approaches to 1 from right side? If you follow the graph, you will see that x approaches to 1 from right side, the y value must be 4. But if you don't have the graph, you can always say, okay, x approaching 1 from right side, that means a number greater than 1. So I'm going to use the first equation, since I should say the number that I'm picking must be greater than 1. I'm approaching 1 from right side. So if you think about the 1, you're approaching from this direction. The x value that you're picking is greater than 1. So you should replace 1 into the first equation. What you get is 1 plus 3, which is 4. And what is the limit as x approaches 1 from left side? You use the second equation, since the number is going to be less than 1. And if you replace 1 there, you get 2 times 1 minus 1, which is 1. So what can I say is the limit on the right side is 4, limit on the left side is 1, and that's what you expect. From the left side, the y value is 1. From the right side, the y value approaches 4. Okay, how about the total limit without any direction? This shouldn't exist, since the right and left limit are not equal. And if the limit does not exist, then you cannot talk about continuity. Because if the function is continuous, this limit must be equal to f of 1. Since f of 1 is simply 4, by the way, f of 1 is 4, replacing 1 into the equation, you get 1 plus 3, which is 4, since you have the equality for the first case. Okay, so what you see is that you have no limit, so there is no necessity to calculate f of 1. But if you found the limit, for example, if the limit was 3, the limit was 3 instead of does not exist, and the value of the function is 4, then you should say still this is not a continuous function since the limit and the value of the function are not equal. But in this case, the limit did not exist at all, so I can simply say, okay, the function is discontinuous at x equal to 1. So this would be a discontinuous at x equal to 1. Any other point, the function is continuous because there are straight lines and it's always continuous. There are some properties that we can mention, I'm going to mention later. There is a theorem. But here is one important thing. If you look at this example, the value of the function is at 4. This is the corresponding y value. Happens at 4. This is the closed point. And if I follow the curve from right side, I'm going to reach to that value. But if I follow the curve from left side, I am not going to be able to reach that exact value of the function. So what we can say about this is a continuous function from right side, since the value of the function and the right limit are equal. If this closed point was not at 4, sorry about that. If this was an open point and on the other side you had a closed point, since the limit on the left and the value of the function would be equal to each other, then you would say, okay, it's continuous from left, not from right. So what we're gonna do is we define the continuity from right or left based on that definition. We say a function f is continuous from right if the right limit and the value of the function are equal. Or we say the function is continuous from left if the value of the function is equal to the limit from the left. Normally, these happen if you're dealing with, again, piecewise functions. But here's a graph just to understand what it means. Okay, so let's look at specific points. Let's say at x equal to -1. Figure out, is the function continuous? So let's look at the continuity at x equal to -1. How does it behave? Let me change this to a different color. So let's go green, for example. At x equal to 1, x equal to -1, what we see is the left limit. Let's calculate the limit. As x approaches to -1 from left side, what do we get? From left side, if you follow the curve from left side approaching to -1, what do you get is the y value is expecting to be 1. If you calculate the right limit, the limit f of x as x approaches to -1 from right hand side, it doesn't mean approaching 1. It means you're still approaching -1 from right side. So I'm still approaching to -1 on the curve, but from the right side. What do I get as the y value is I expect the y value to be 2. So now you should say that, okay, the limit of the function as x approaches to -1, it doesn't exist in general, since the right and left limit are not equal. But what I can say is, okay, this is not a continuous function at -1, but there may be a continuity from right or left. So what do I do is I check to figure out what is f of -1. That means at -1, what is the exact value? At -1, here's a close point. The value of that is 1. Now check. What is this value equal to? It equals to limit on the left side. That means the left limit is the same as the value of the function, which means if we have continuity on the left side. So this is left continuous. The function is continuous from left side. That's what you can say. Since the left limit is exactly the same as the value of the function. How about if we try another point? Let's say at x equal to 2. How about continuity at that point? Again, you go through this procedure. You calculate limit as x approaches to 2 from left. What happens? If I approach 2 from left, you'll get the y value of 1. if you limit f of x. And if you calculate the limit f of x as x approaches to 2 from right side, what do we get? We approach 2 from right side, still the y value is approaching 1. So I can say the total limit as x approaches to 2 from either direction, it should be 1 since these two are equal to each other. But what is the value of the function? F of 2 at the point 2, y value is this closed circle is 2. What does it mean? That means the limit, which is 1, is not going to be equal to the value of the function. The limit at 2 is not the same as the value of the function. These two are not equal to each other. So I can say the function is not continuous. Is it continuous from either direction? Not really, since the limit is 1 on both sides. They're never equal to the y value of the function, which is 2. And if you look at the graph, both side limit will approach to some value of 1, but there is a closed point nowhere close to that y value of 1. So at 2 we have total discontinuity. There is no continuity from left or right either. And if you look at 5, right limit and the value of the function are equal to each other. So what can I say about x equal to 5? We have right continuity. You can calculate, okay, what is limit of the function as x approaches to 5 from right side? It is y value of 0. This is on the y-axis, on the x-axis. And the value of the function at 5 is exactly 0. These two are equal to each other, so therefore we have the right continuity. But the left limit f of x as x approaches to 5 from left side, this is a different number. This is y value of 3. If you approach 5 from left side, that means follow the curve from left side. What you get as y value is 3. Okay, so these are examples that you can see that the function is continuous from right or left, or maybe discontinuous totally. Here's a big theorem that helps reduce the work. So it means that you don't need to go through all the points if you're looking for continuity or discontinuity points. Let's assume we have two functions, f and g, and they're both continuous at a specific point A. Then any combination of adding those two functions, subtracting the functions, or multiplying them, dividing them by each other with the assumption that the denominator is not 0, or multiplying the function by a constant, still holds the continuity at that point. So if you have two continuous functions, any operation of addition, multiplication, division, or multiplying by a constant does not affect the continuity. So in general, when we have polynomials, they're built based on constant and linear function, which is kind of continuous. Just by looking at the linear function, you have continuous function. So polynomials should be continuous everywhere, since they're multiplication of linear functions with itself, or combinations, addition, subtraction, or something like that. On the other side, rational functions are this division form. You have function polynomial divided by another polynomial. So the only thing that you need to check if you're dealing with rational function is to figure out where the denominator is 0. If the denominator is 0, that point is undefined for the function. So what we do is we can say, okay, the function is continuous everywhere in its domain. The points that do not belong to the domain, you have a discontinuity. And similarly for the root functions. Root functions are continuous everywhere in the domain. If you get negative number underneath the square root, you cannot discuss the value of the function. So it's not possible. So for the root function, as well as the trig functions, as long as you have the point in the domain, you can say the function is continuous at that point. So if you're looking for the discontinuity for any of these types of functions, you just figure out the domain. You can find out that the function is continuous everywhere in the domain. Here's an example of combination of trigonometry and rational functions. So here, find the limit of this function. Okay, let's replace pi half into the function. Can we do that? If we try to replace pi half into the function, what we get is sine pi half divided by 2 minus cosine pi half as x approaches to pi half. Sorry, there's no limit anymore since we evaluated. If we do this, what we can say is sine pi half is simply 1, cosine pi half is 0, 2 minus 0, so we get 1 half. Why would this be possible? This is possible since we know that x equal to pi half is in the point in the domain, and either one of these functions, sine x is by itself continuous, 2 minus cosine x is continuous, so therefore the limit and the value of the functions are equal. So it's not necessary for us to draw tables and pick points close to pi half. We can simply calculate each value and make sure as long as the denominator is not 0, you can say, okay, since the combination of these functions are continuous, their division must be continuous at that point, as long as it doesn't make the denominator 0 again. So therefore the limits must be equal to the value of the function. So if I evaluate the function at that point, it must be equal to the limit. This is not true if you were dealing with something like this, sine x divided by, I don't know, x minus 1 as x approaches to, let's say x minus pi, as x approaches to pi. You cannot say, okay, let's replace pi and say, let's change this to pi half. You cannot say, let's replace pi half minus pi half. This would be 1 divided by 0. This is kind of impossible to evaluate. So you cannot say this for this specific case, since it makes the denominator 0. If the denominator is non-zero, you can simply evaluate the function, just because it's a combination of continuous functions. Okay, so this was a consequence of the fact that rational functions and trigonometric functions are both continuous, so their division must be continuous, so therefore the limit would be exactly the value of the function. That's what this last example was about. And finally, this is one of the useful theorems in calculus to finding zeros of a function, intermediate value theorem. It uses the property of a continuous function. So let's assume f is a continuous function on an interval a to b. And let n be a number somewhere between f of a and f of b. Let me show you this. Okay. So we assume we have a function over this specific interval a to b. And what is the property of that function? And we say the function is continuous. So there is no jump in the function. The function might behave something like this. As long as there is no jump into it, it doesn't really matter. Okay. Let's say f of b, the endpoints, f of a is here, f of b is there. So somehow these 2 points must be connected to each other since the function is continuous. And you cannot do this something like this, otherwise this would not be a function. What you can do is you can say, okay, maybe it behaves somehow like this. It doesn't really matter how you draw it, as long as you connect these 2 points. So I'm going to do the simplest case. And it says, let n be a number between f of a and f of b. So here's f of b, here's f of a. Let n be a number in between. So I pick the n somewhere here. What can we say is, since you connect these 2 points together, f of a and f of b, that means there must be some value in between. With the x point of c, let's call this c, where f of c is exactly n. So this n is exactly the same as f of c. Any way you connect this curve, there should be such a point. In this case, that would be the point. But I'm going to pick this drawing to be the simplest so you can explain it. So there is always this point, at least one point. Maybe the curve goes around and comes back, something like this. So there are multiple points with that y value of n. Okay, but at least there is one point where the y value is exactly n, as long as n is between f of a and f of b. This is one property of continuity. And why are we using this? Let's assume that you know that f of b is positive and f of a is negative. And I'm going to pick this n to be 0. That means I know there is a point where the function has a y value of 0. And where is that point? Somewhere when it crosses the x-axis. So as long as I know I have a y value positive and a y value negative at the endpoints, I know there must be a point in between a and b where the value of the function is 0 at that point. Since the function has to cross the x-axis. That means any type of function that you draw, as long as you know endpoints, one is above the x-axis, the other one is below the x-axis. However you connect these 2 points, you must always cross the x-axis. At that point, you have a y value of 0. You can draw it this way, with multiple zeros. As long as you cross the x-axis, you show that there is a point where the function is 0. We use that property here in this example. It says, consider this function f of x, x cubed minus 2x plus 1, and show that at least there is a 0 in this interval 1 and 2. What you need to show is that, figure out what is f of 1. If we evaluate f of 1, it is 1 cubed minus 2 times 1 plus 1. This is actually maybe not a good example since it becomes 0. So let me erase this 1 at the end. Okay, let's do this. f1 is already a 0, so that's why I didn't pick. So f of 1 would be negative 1. If you evaluate f of 1, you will get negative 1. What if you evaluate f of 2? What we get is 2 cubed minus 2 times 2. It's 8 minus 4, you will get 4. That means if you draw the function, you have at 1, you have y value of negative 1. This is the y value of negative 1. At 2, you have y value of 4. And since this is a polynomial, it's a continuous function. So somehow these 2 points are connected. Maybe like that. Maybe like this. We don't really know how it behaves. But we know that there is a connection between these 2 points. I'm going to pick the simplest case again. You don't need to draw the curve. I'm just going to show you that I can say, okay, since one of the y values is positive and the other y value is negative, therefore there should be a point by the intermediate value theorem where the y value is 0 in between negative 1 and 4. So you can say since 0 is between negative 1 and 4, therefore by the intermediate value theorem there is a c such that f of c is 0. Whatever that c is, it should be between 1 and 2. C between 1 and 2, I should say. And maybe I should say in the interval 1 to 2. Okay, so this is a consequence of the fact that you have a continuous function. If the function f was discontinuous, you may not have this property. If the function was discontinuous, you could have something like this. This is possible, and you never cross the x-axis. But since we assume that the function is a polynomial, in this case given, the continuous function, so therefore you should cross the x-axis. Okay, this is a consequence of this, a very important consequence to figure out zeros of functions. Numerical analysis, I think there was a method, Newton method or something. You divide the intervals and keep going and to figure out the zeros of the function. This is very useful. Okay, I'm gonna stop at this point. Hopefully next time we start chapter 2.